So let me remind you that a sequence is an ordered set of numbers, real numbers, in calculus. So the technical definition was that it's a function from integers to real numbers. The notation is generally, this is the general notation. We denote this A0, A1, etc. You have to give a way of understanding the general term. Okay, there has to be, it must be well defined. Sometimes you start from A0, sometimes you start from here. The first part is not important. The important part is this part called the tail of the sequence. We want to understand the behavior of the tail of the sequence. Do those numbers behave as if they are getting closer and closer to another real number? That's the question here. Okay. So we say limit of this sequence as n goes to infinite, so in that part is equal to L if for any epsilon positive, there are, so this is not the technical definition, this is an equivalent way of seeing, because I gave the technical definitions the other day. So this is how in real life you notice these things. There are only finitely many an outside the interval. Okay, so this is L plus epsilon, this is L minus epsilon. Okay. So it's not only that infinitely many of the terms lie in this interval. There are those that are not inside here are only finitely many. Okay. So no, this is the catch point is here. No matter how small an interval you choose around this number L, there are only finitely many elements that are not inside that interval. That finitely many may be a huge number, but only finitely many. Okay, so this is the actual understanding of the limit. And what other things? There's another way to see this limit. Okay, so we define a subsequence. Okay. Of course, it is important. It is equally important to see a limit exist as to see that a limit does not exist. So one way to see a limit does not exist is the following. We define subsequence, a subsequence. Okay, so we have our sequence, say A0, A1, A2, etc. A subsequence. So you choose this one, you call it B0. You choose A17, you call it B1. Okay, you choose A100, you call it B3. Okay, so like this you make a choice. Okay. Choose infinitely many an in the given order. Okay, so you don't change, you don't make this before this one. You just continue from here, and from time to time you choose one of the elements of the sequence and give it an index. Okay, so this is a subsequence. Okay, let's see what happens to a subsequence of a convergent sequence. If this is the limit, you choose an arbitrary epsilon. There are infinitely many elements here of an, and there are only finitely many outside. Say there are only 1,000 elements of an outside here. Now I choose this subsequence. Obviously now almost all elements of Bn are here, and at most 1,000 elements are outside. So this sequence Bn also converges to the same limit. Okay? So if limit n goes to infinity is L, then for any subsequence, Bn. Okay, so there are different notations for the sequence. Sometimes they put a bracket around this, sometimes they put arrow. Okay, I'm using this notation Bn to denote both the element En and the sequence Bn. Okay, the context will make it clear. Okay, so then for any subsequence Bn, we also have limit Bn as n goes to infinity is equal to L. Okay, so that's obvious, but for most obvious statements, you turn the statement around and it becomes a very useful statement. Suppose now you have two subsequences which converge to two different limits, then you know that this sequence cannot converge to a limit, okay? Because then it will violate this totally obvious condition. Okay, so from this, we develop a criterion for divergence. Okay, so if a sequence has two subsequences converging to two different limits, then the sequence itself is divergent. Okay. Also, you can say that if a sequence has a divergent subsequence, then it is divergent. Okay. Also, if a sequence has a divergent subsequence, generally the divergent subsequence, which is easy to notice, is something that goes to infinity. Okay, so in this sequence, you find elements just dispersed around there, which become larger and larger. Okay, so that subsequence is going to infinity. Okay, so that's how you notice this, in particular, diverging to infinity. So this is, in general, what we notice. Then the sequence, again, the sequence itself is divergent. Okay, so this is one of the easy ways to detect a sequence is divergent. Okay, so I think I'll give an example after this. Okay, so for example, let's have an easy example. Now consider the sequence A0 equals, say, 5, and an is equal to 1 over an minus 1 for n greater than or equal to 1. Okay, now looking at this one, okay, taking limits of both sides as n goes to infinity, and of course assuming the limit exists, we take the limit of an. Okay, so say limit an as n goes to infinity is equal to 1 over limit as n goes to infinity an minus 1. So assume that the limit exists, and this is L equals 1 over L. Okay, so this gives you L squared equals 1. Okay, so L is equal to plus or minus 1, but all ANs are positive. Okay, so this is positive. You take the reciprocal. You don't introduce a negative sign. So L must be greater than or equal to 0. Hence, L is equal to 1. Okay, so what we calculated here is if the limit exists, then it must be 1. Okay, but if the limit does not exist, then You just did that calculation for nothing. Okay, so what we found is okay, if the limit exists, it must be 1. Okay, now let us check if the limit exists or not. The sequence is we start with 5, then we take 1 over 5, then we take 1 over 5, which is 5 again. Okay, so this is the sequence. Okay. A subsequence is 5, 5, 5, 5. This converges to 5. Okay, every constant sequence satisfies all the definitions, all different definitions of limit, and it goes to 5. Another subsequence, 1 over 5, 1 over 5, 1 over 5. This goes to 1 over 5. Okay, different limits. Okay, so from here, so the sequence is divergent. Okay, so this is why it is important to check if the limit exists or not. Otherwise, algebra always gives you a nice number. Okay, so algebra has this if in it. So algebra says, I don't take any responsibility. Okay, so the responsibility is yours. Now you tell me to do these calculations, I'll do those calculations. You want a number, here is a number. Okay? But then it is your responsibility to check if this number makes sense. In this case, this number does not make sense for this thing. Okay, so this is one example. Another thing is, of course, some sequences are defined reductively. You define the sequence, the next element, depending on the previous elements. In that case, in order to understand the general behavior of the sequence, you have to do some induction. So let me talk about mathematical induction briefly. Okay, so some sequences are defined recursively. Okay. In most of these cases, in those cases, we generally need induction to understand the sequence. Okay. So what is mathematical induction? So mathematical induction is like domino tile games, toppling games. Okay, so what you do is remember that on a table they put these domino tiles together. Okay. They do lots of these things. And then you hit the one, you topple the first one, it hits the second one hits, and this goes on. You see these on YouTube. Okay, so they spent 2 or 3 days setting this up, and then in 15 minutes, tens of thousands of these things are toppled. Okay, then everybody is happy for some reason. Okay, why does it work? It works for 2 reasons from a mathematical point of view. Okay, so here you place the tiles such that if the previous one is toppled, so I will write this, toppled, then the next one is also falls. The next one also falls down. Okay, let's say we can visualize it. Okay, So this, in mathematical terms, if our statement is true for n, then it is true for n plus 1. And, of course, the most important thing is somebody hits the first one. Hits the first tile. Okay? So these are the two things that you keep in mind when you are placing these domino tiles. Okay? So if these two conditions are satisfied, then then all of the domino tiles are down. Okay? So we mimic this one. So we want to prove, we want to check if a statement, say Pn, is true for all n. Okay, all n, let's say, larger than or equal to, in our case, let's say 1. Okay, so this is, in our case, this is going to be, for example, each term of the sequence is positive, for example. Okay, so you check if the first term is positive. Okay, check. So this corresponding to this one. So let's say 1. Check if P1 is true. Okay, if it is true, then you pass to the second one. Okay. Check if P1 plus 1 is true when Pn is true. Okay, so it is this one. Sometimes we use a modified version of this, okay, because it's also mimicked here. Check if Pn plus 1 is true when P1, P2, Pn is true. Okay, so let me go back for a minute. Check if this is true when Pn is true. So this n must be larger than or equal to what you hold here. Okay, so in our case, I'll write this one. But sometimes your statement starts, say, from n equals 5. Okay, then here you have to show that this implication is true and n is larger than or equal to 5. Okay, so what can go wrong here? Okay, let's again going back to this. You check that P1 is true, and then you show that Pn plus 1 will be true when Pn is true when n is larger than or equal to 5. Okay, so it doesn't, those two things do not match. Okay, because P1 is true, but using P1 is true, you cannot show that P2 is true because your implication here starts to work when n is larger than or equal to 5 in my example. Okay, so that is something that you have to pay attention. And sometimes you need to use this one. These two are, for our purposes, the same because that's also what happens here. By the time we come here, all the files here are down, so you can use it. They are all hit down. They are all down. So using that information, can I show that this one will also be hit? Okay, so this is a mathematical induction. The difficult thing in mathematical induction is generally to find out what to prove. Okay, so given Pn, then in most cases you can try a little bit and show that it is true. But how do you find out Pn? Okay, so that's when you play with the equations and you have to come up with something. And there are lots of examples in the books, in elementary books, where P1 holds, but this doesn't hold. Or you can show that there are more, these are more interesting examples. You can show that if it holds at any point, then it will hold everywhere. You have such wonderful statements. If it holds at any point, it will hold everywhere, but it doesn't hold anywhere. Okay, so you cannot ignore any of these. You have to prove, you have to check both of these conditions. Okay, so let's start with an example where we will use these things. Okay, here's a famous example. Okay, start with any two real numbers. So start with any two positive real numbers A and B. Okay, so I emphasize that they are positive. Define a sequence as follows. Okay, so R1, let me see if I start with R1 or R0 because, okay, R0 I think. Because the choice of index makes life easier later on. R0 is A over B. R1 is A plus 2B over A plus B. Okay. So if Rn is equal to Xn over Yn, then Rm plus 1 is equal to Xn plus 2Yn over Xn plus Yn. Here, this is n greater than or equal to 0. Okay, so the question is, does the sequence converge? And if so, where? Okay, so question. Limit Rn as n goes to infinity is what? When you say it is what, so you are also asking the question if it exists. Okay, so does the limit exist? If it doesn't exist, we are done. If it exists, then what is the limit? You see, from here we can immediately find the limit if it exists. Okay, so suppose the limit exists. Limit Rn as n goes to infinity is equal to L exists. So that means this number L is a finite number. Then we start from here. Use Rm plus 1 equals Xn plus 2Yn over Xn plus Yn. So what is happening here? I can write this thing as Xn plus Yn plus Yn over Xn plus Yn. Let me see, I did something here. I have to do a few more work here. Okay, so this is. So, okay, so I'll write this one in between. I have to write some. You see, there is no algorithm to solve such things. You just play around. I can also continue from here, and after a few minutes work, I can get the limit. But there's a short way. I did this at home, so let me do the short way. Okay, so this is my definition. And in the definition, I wrote exactly what I did before. So, yeah, okay, so I understand what I did now. Okay, so let me start. The thing that comes to your mind is first is the correcting, as in the test. Okay, now divide everything by Yn. Okay, so Xn over Yn plus 2 over Xn over Yn plus 1. Okay, then use this definition. Rn plus 2 over Rn plus 1. Okay, now take the limit. As n goes to infinity. Okay, so I'll have L here equals L plus 2 over L plus 1. So here I have L squared plus L is equal to L plus 2. Okay, so I cancel these. I have L squared is equal to 2. You see, I started with positive numbers. I'm just taking quotients, etc. I'm not introducing a sign anywhere. So these things will never be negative. Okay, so Rn's are all positive. In fact, they are all strictly positive. Okay, so L can be at least 0. Hence, L is equal to square root 2. Okay, so if the limit exists, it is square root 2. So the surprising thing here is that no matter which numbers a and b, no matter which two positive numbers a and b you start, this thing converges to square root 2 if it converges at all. Okay, so now we have to check if it converges. Okay, so next, check if the sequence converges. Okay, so how do you check this? There's no rule here. You have to play with the general expressions here. Okay, so you have to play with this thing here. Okay, so first thing, after you do this, you will eventually need to find out that both the numerator and denominator are going to infinity. Okay, so you see, every time you are adding something, every time the numerator of this is larger than the numerator of the previous one, the denominator is larger than the previous one, you are always adding something positive. Okay, what you add is increasing, so the numerator and denominator are both going to infinity. Okay, so we'll eventually need this. So in fact, in the proof, we'll need that yn goes to infinity. Okay, so note that. Okay, so claim yn is larger than, well, certain things I don't have to remember. Yn is greater than, well, generally I put greater than or equal to, because if you want to say strict inequality, you have to prove something extra, that they will never be equal. We don't need that. I want to show that this goes to infinity. So this is b to the power n, I think, no, 2 to the power n b. N greater than or equal to 0. Okay, so this is our claim. So if the claim is true, you see yn goes to infinite. We'll use this in the proof. Okay, so when n equals 0, y0 is equal to b. Okay, so this is equal to 2 to the 0 b. So the claim is true for n equals 0. So assume that the claim is true for all k less than or equal to n, and show the claim for m plus 1. Okay, so for m plus 1, I want to understand why m plus 1. The only thing I know about yn plus 1 is that it is equal to xn plus yn. Okay, so I think, what do I do from here? Okay, so yn is xn plus yn, but no, this. Okay, xn, so I need to put one more thing. Xn here is, for the previous one, xn minus 1 plus, so this one, I'm concentrating on this one, xn minus 1 plus 2yn minus 1. Okay, so that's for xn plus yn. Okay, so I think now it works. Now xn plus 1, everything is positive here, so this is larger than or equal to 2yn minus 1 plus yn. Now I use the induction hypothesis. So this is what we call induction hypothesis. If you cannot spell the word hypothesis, you can say induction assumption. Okay? Because at every step you have to explain to yourself why you are doing this. The reason why we are doing this is because we are using the assumption. The assumption says that, okay, so this is 2 times yn minus 1 is larger than or equal to 2 to the power n minus 1b. Plus, according to our assumption, this is 2 to the power n. This is larger than or equal to 2 to the power n b. Okay, so you see that this part is now equal to 2 to the power n plus 1b. Okay, so this is 2 to the n. We have 2 of these 2 to the n. We have this. So we have this is, okay, so less than or equal to this. Okay, hence, by induction, yn is larger than or equal to 2 to the n b for all n larger than or equal to 0. So from here, we know limit yn as n goes to infinite is equal to infinite. Okay, so let us not forget what we were trying to do. We were trying to show that this limit exists. Okay, so for that thing, we'll find a trick. We have another, after you play with the equation, you find out that the following equality holds. So, okay, so we have another claim. So we say that xn square minus 2yn square is equal to minus 1n over a square minus 2b square for all n greater than or equal to 0. Okay, so maybe I must remind ourselves that 0 is a over b, and r1 is a plus 2b over a plus b, etc. So this goes on like this. Okay, so for n equals 0, we have x0 square minus 2y0 square. Well, this is equal to a square minus 2b square. So this is equal to minus 1, 0, a square minus 2b square. So claim is true for n equals 0. Okay, so now assume the claim for n, check if it is true for n plus 1. Okay, so let's see. Now for n plus 1, I'm trying to understand xn plus 1 square minus 2yn plus 1 square. Okay, so this is what I want to understand. Now for these things, I have the rules. Xn is equal to, xn plus 1 is equal to xn plus 2yn square minus 2 times. I also have a formula for this. This is xn plus yn square. So we reduced it to the previous case. Now, if there's a relation among these, I'll be done. So let us write this. This is xn square plus 4xn yn plus 4yn square minus 2xn square minus 4xn yn minus 2yn square. Okay, so these things cancel. And what do I have? I have xn, so I have, this is equal to minus xn square. Then I have this and this, so this is plus 2yn square. So this is minus xn square minus 2yn square. Assumption, okay, so assumption, induction assumption. Minus, so this thing is here, minus 1 to the power n, a square minus 2b square. Okay, so that is now minus 1 n plus 1, a square minus 2b square. Okay, so so this proves that the claim is true for n plus 1. So, okay, hence the claim is true for all n larger than or equal to 0. Okay, so how do we put these things together. Now we found out that if the limit exists, it is 2. So we check if that is really, if the limit is really. Okay, so now that we suspect that the limit is 2, we can start the following. Okay, now we can try Rn squared minus 2. I want to show that this limit is equal to 0. Okay, so how do I suspect 2 here? Because that's what I did. Now I'll play with this one. So let us see. If you write this thing, this is xn squared over yn squared minus 2. If you do this, this is xn squared minus 2 yn squared over yn squared. Now I use the fact that our claim, we proved this claim. We proved this claim. So this thing is equal to minus 1n a squared minus 2b squared divided by yn squared. Okay. Now we take the limit as n goes to infinity. Now here, this is the whole idea of doing this is that this part is bounded. Now this part, a squared minus 2b squared, does not depend on n. It's a fixed number. Only its sign changes. So if I take the absolute value of this, okay, so I take the absolute value of this, I have a squared minus 2b squared divided by yn squared. So a constant number divided by a sequence which goes to infinity. Okay, so this goes to 0 as n goes to infinity, since limit yn as n goes to infinity is equal to 0. Okay, so that's why we check that trivial fact that yn increases beyond bound. You need it at this step. Okay, so we proved limit Rn as n goes to infinite is equal to 2. The limit exists, and it is equal to square root 2. It is equal to square root of 2, as we found over there. Okay? So this is, it looks like it's a bit long, but compared to typical problems in mathematics, this is a very short problem. Okay, so this was one problem. Let me see if I have. Okay, I have lots of such problems. But let me continue with the following thing. So remember that we had the following thing. If we have a sequence an, and we see that by looking at the formula of this, instead of n, if you put x, you get a nice function. We see that there is a function f of x such that f of n is equal to an. Okay? Then limit f of x as x goes to infinity is the same thing as limit as n goes to infinity of an. Okay, so this is where we tie this theory to the theory, the usual theory of calculus, where you can now take limits. Most of the time, if you cannot immediately see what the limit is by just looking at the formula of this, it means that it is an indeterminate form. Okay, so it's probably a rational number where both the numerator and denominator either go to 0 or go to infinity. So it's not easy to define which one wins. And then you use L'Hopital. Okay, so this is the bridge that tells us that we can now pour all differential techniques of calculus into this sequence, even though this part is digital. Okay, so later on maybe you will take discrete math where you will see that you will only be working with the integers, so calculus does not apply there. You have totally different techniques. But in this particular example, because of this link, calculus applies. Okay, so this is a special case of discrete math. Okay, so we are interested in these things here now. Remember also that we are doing these sequences not for fun, even though there are books only on sequences because there's lots of fun. If we have time, I'll show you very interesting sequences next hour. But we are going to do this to understand series. And in series, there are certain common limits, common sequences that arise very frequently. Okay? So we have to check some common. There are some frequently appearing patterns here when you study a series. So now we have a list of these things. I'll go over them quickly because this is on Moodle. I think you all have downloaded this and printed it out. But okay, I'll go over these things because these are important. So for any constant x whose absolute value is strictly less than 1, the limit x to the n as n goes to infinity is 0. Okay? Well, this is easy because you keep multiplying x by something smaller than 1, and it's not difficult to show that it goes to 0. If x is equal to 1, then the limit is 1. That's also trivial. If x equals minus 1, then it oscillates between plus and minus 1. So it has a subsequence that converges to 1, another subsequence that converges to minus 1. So the limit does not exist. If x is larger than 1, if it is positive and larger than 1, it goes to infinity. If it is negative and its absolute value is larger than 1, okay, so then its absolute value goes to infinity. So one subsequence goes to plus infinity, the other subsequence goes to minus infinity. So this is the only case where we have a reasonable limit. Well, you are surprised that we mentioned this, but when this thing suddenly comes up in the middle of a very complicated problem, and then you don't believe that the answer is 0. Okay, so that's why we make it a theorem. You have to remember that no matter where it appears, this is 0. Okay, so the second thing is, again, easy. So for any constant x positive, you have a limit x to the power 1 over n as n goes to infinite is 0, is 1. Because this goes to 0 and it makes it 1. And when x is negative, that's something in complex analysis. We are not entering into that. Okay, so this one is important. This will show up very, very often in series. Limit as n goes to infinite. You have to do it one way or the other. Xn over n factorial. Okay? No matter how large x is, okay, eventually n will be larger than because n is going to infinity. Okay, so from that point on, you start dividing x by numbers larger than x. So you suspect that this thing goes to 0, and it does go to 0. Okay, so in this handout, you will see a short explanation about why it goes to 0. And well, this one is important. You have to keep this in mind. This will show up very often as n goes to infinity. 1 plus x over n is equal to e to the x for any x. Okay, so actually we did this last semester, I think, when, well, instead of x, you put a constant here, and then instead of n, you have x. Take the logarithm, then take the limit, apply L'Hopital, and you will see that you get the limit as e to the limit in that case will be x. Okay, since you took the logarithm, the actual limit will be e to the x. Okay, so there are exercises in the book. If you consider the sequence where this is an, okay. For example, when you put x equals 1, this sequence will converge to e. Okay, so you have to use a little bit trick to show that this sequence, I think, increases to e. Okay, so that's a good, that's a cheap way of obtaining decimal expansion of E. And so this one also is very typical. Limit as n goes to infinity, n to the power 1 over n. Okay, so this will show up very often. Now this is really tricky because the power goes to 0, so 0 power of anything is 1. But the base goes to infinity, so it says let's get larger and larger. So which one wins here? So that's the problem. Okay, but the general rule here, the mathematical rule, is that exponentiation always wins. Okay, so if you bet your money on that, you never lose. Here the exponential says I'm going to 0, so I'll make everybody 1. Okay, so you stop there. You don't ask anybody else. This goes to 1. Okay. So how do you prove this? You again take the sequence, take the logarithm of this. When you take the logarithm of this, then it's a typical case for applying L'Hopital. You apply the L'Hopital, you find the answer, and then you exponentiate, you get 1. Okay? And we have, so I think I missed the numbers, but anyway. And we have this one. So this one is actually follows from this one. Where is this thing? Okay, limit n goes to infinity, ln n to the power a over n to the power b. So here you have a and b, any positive in numbers, real numbers. So for example, this can be as large as you like. This can be as small as you like. The limit is always 0 because, again, another rule. If logarithm is fighting against anybody, it loses. Okay, so here there is the logarithm. Logarithm goes to infinite. Some huge power of this goes to infinite, but nobody has seen logarithm beat up anybody, so it will lose. This is a polynomial. Polynomial will win. Okay, if polynomial fights with exponential, exponential will win. So this one is 0. Again, you do this by applying L'Hopital several times. You see, when you take the derivative of this, 1 over n comes. 1 over n compensates for the n lost here after you take the derivative. Okay? So when you take the derivative, this b, after you apply L'Hopital, you take the derivative of this and derivative of this. This poor guy loses a power. It becomes a minus 1, but this is still b. Okay? What it lost is given back by this one. So after you repeatedly apply L'Hopital, this one becomes 0 or negative. In that case, this is still n to the b. So in that case, it easily seen to go to 0. Okay, so the next one is interesting, so I'll mention that. So this one is, this will also show up. N goes to infinity. So let me see which version we are doing. You take n factorial and take its nth root, and then you divide it by n. Surprisingly, this is not 0, not infinite, not 1. It is 1 over e. Okay, so the most general case is known by Stirling's formula. Stirling's formula. So this is a spectacular formula. People are still trying to find shorter and shorter proofs of this, but the shortest proof of this was 2 or 3 pages, but in order to fill in the gaps, you had to write 5 or 10 pages of notes. So there's no short proof of this, but it is true. The proof is, the Stirling's formula is this. The idea in this type of thing is to understand how n factorial behaves. Okay, so there is in analysis, there is the gamma function, which continuously explains n factorial. And gamma function is important because we have this Riemann zeta function, which is a $1 million problem. We are interested in the zeros of this, etc. Okay, so n factorial is important in mathematics. So we are trying to understand how n factorial grows. So Stirling's formula tells us that as n goes to infinity, n factorial behaves like what we write here. So this is square root 2 pi n. Okay, so pi appears here. And then n over e appears here to the power n. Okay, so and this is equal to 1. It means that asymptotically, when n is very large, the value of this is almost the value of this. Okay? So if you assume this, put it over here, you see I want to take the nth power of this. If you take the nth power of this, I get this. If you take the nth power of this, this is gone. So I have n over e here. You have n over e here. If you take the nth root of this, you see I have this one. Okay? So the only thing here is n to the power 2 over n. Okay? So that goes to 1. 2 pi is a constant. Okay? So there we are here. That goes to 1. So when you take the nth root of this one, it contributes 1. When you take the nth root of it contributes 1. So Stirling formula tells you that nth root of this divided by this is equal to 1. Okay? Here you have this constant. You take it to the other side. That is 1 over e. Okay? So this is the actual proof of this. But there is an explanation here about how to prove this using okay, let's take a break. I won't give the proof of this because the proof is explained. There's a cheaper way of proving this without converting this. You look at the area under y equals ln x. Okay, so then you also get this one. Okay, so these are the sequences that appear frequently. Let's take a break, then I'll solve some more problems.